Welcome, I'm Bill Wake. We're working on a compiler slash interpreter for a language called Tenth that's an imitator of Fourth. And we've basically gotten through most of the compiler except this piece about compiling strings. So we'll focus on that today. And when we finish those, we have some operators to work on, or operations. And then I think we'll switch to trying to do input. I don't think we'll get that far today, but we'll see. All right, we're working in ARM assembly language, 64-bit. We're using Xcode just mostly as an editor, and we're using TDD, test-driven development. I believe we left everything running in green. Okay, so I don't see anything that looks like a problem. Good. All right, so compile time strings. Let's see, that's going to be in REPL. Okay, yeah, here's eval. Okay, so we added something to take care of the case where a string was found in eval, which is the routine that does runtime evaluation, kind of while you're editing, the REPL aspect. We've not done the compiler side. So basically, if you try and execute some sort of command word, it decides, are you the kind of word that gets compiled or the kind that gets evaluated? Okay, now eval has that check for a string and then treats it specially. Compile does not. Okay, it checks for a number. Well, it checks for a word and it checks for a number, but it doesn't look for a string specifically. So our read word method is returns, I guess you can see it best in eval, it returns x1 is a type, which could be string found. X0 is the actual string. In our case, with quote marks stripped off. Okay, so compiling these things, all right. Well, the way our setup works, I guess I'll just paste stuff in here. We have a header, and the header, first of all, consists of a dictionary pointer. So these words are in a linked list, and it finds them from that. Okay. Then we have a name. Well, it's a pointer to a name, and we have a pointer to. It's kind of a pointer to a function, and then we have the body. Okay. Now, the strings, well, this all goes on as you define words, those get filled in. But we're going to put strings in the same space. We have to manage their contents and make sure they don't make this stuff hard. So we have a word that does that, or a function that does that. But for strings, it's going to be different. So strings, like from the previous word, you would see an N2D. That's the last part of its body. All right. And now for a string, we just want to put the contents of the string. But we also have to follow it with buffer bytes. I don't know the right word for it, but most of our pointers and words we want to access on 64-bit boundaries because 64-bit machine. Strings don't do that. They have, well, if there's lots of ways to represent them, but at least one way is a sequence of bytes followed by a 0 byte for an empty, a nil, so that we're using C's 0 terminated strings. All right, let me. And so those strings, they can be arbitrary lengths, but we have to, I guess maybe padding might be a better word. we need to make sure it gets back on an 8-byte boundary. So when we go to put the next dictionary pointer in, that thing lines up on an 8-byte boundary. And then we'll keep track of the start of this thing. String start, maybe think of it as a label, though there won't really be one, but we'll have that pointer to the contents of the string is going to be the result of of compiling a string. Okay, now the trick for compiling is, well, we're in the middle of creating a body at that point. Okay, so I think what we're going to do, I don't know, I know I took some notes somewhere, so let's find those. And then I think it'll all make more sense. Okay, yeah. Oops, just this one. Well, let's just move it up where we are. Okay, so because here's that same secondary, we've got, previous routine names that we're going to do, but then we have to put the string somewhere. Well, we can't put it between, we can't put it before this word because we've already put other stuff there, and we can't put it after because we don't know where to put it yet till we get to the end. So I think what we'll do is we'll do a little trickiness to put it in the middle. And so we already have a word push that's used as kind of an internal thing. So if you say 7, then we just push 7. It gets translated. So I want to do the same thing, push, and then I just want the address of the new string. Well, that's going to be a little ways down. We're going to put it in, but we're going to jump around it. All right, so when I'm here, I can generate the push. I know where, well, secondary space is pointing right here at that moment. I know where to go from there, +8, +16, +24 to get, 3 words down. Then I've got to jump, and I'm going to jump around it. Well, I can't jump around it until I know the actual contents of the string. But once I do, I can, well, I guess I could work out a function from the length of it as well. But one way or the other, I need to backfill this -1 with the actual pointer that points after the string plus its padding bytes. All right, and the alternative we have, or an alternative, would be to create a separate space strictly for strings. I don't think that's worth the work. The cost of these couple of instructions is just not super high, and it's just like one less space to manage. We'd have to have a register pointing to it somewhere and keep track of it, and know where it starts, know where it ends, and all that good stuff. So it brings a fair bit of complexity compared to just putting the string here and not worrying about it. Most strings, if you're working with a string, you're probably either just going to print it, or maybe you're going to append some stuff together to make something. I don't know, whatever it is. But the actual constant, I don't think it's going to get initialized that many times, which means we're just spending, a few words of space for these instructions, but I don't think they'll become a bottleneck for you. If they did, you could just create the constant above the loop, and don't create constants in loops, or don't create unnecessarily new values inside a loop. That's a pretty standard optimization. Okay. All right. So I almost kind of laid it out here. We want this string at compile time. We're going to create the string and push its address on the stack so the user gets the pointer to the string, and then generate the push, generate secondary space, which is currently pointing right here. +24 is going to be where the string starts. Generate a jump instruction. Then we'll put the new secondary space. We'll generate a -1, but put that address onto the control stack. Then put the string itself filled out to 64 bits. Now secondary space points to where that jump should go, so we'll pop that and patch this entry. Now we could compute, if it's exactly 7 bytes plus one for the zero, okay, well, we know it's one word down and stuff, but I think we'll take the lazy way and just, we'll take the time to push that address on the stack and backpatch it rather than trying to pre-compute it and risk having two ways to do something. Okay. Let's see. So we want to test drive this. I think this kind of, this is kind of our test case, really. I'm going to put a string in, maybe follow it by one word, and make sure that the contents of the secondary is push some number, jump some number, string, the thing jump to, and then whatever, maybe we'll put a print or something, I don't know, but something will be there. Maybe N2D. I mean, honestly, we don't need to do too much. Okay, so let's build a test for this. It's kind of it's a fair bit of work, so I think we're gonna do a little bit of we'll extract a method for this. It's a little complicated. Okay, so we should have REPL tests somewhere. All right, let's get those over here. And I think we'll just close the stuff to the right. Okay, this was kind of explanation. Okay, so the test is, I think it's compile string puts it after jumps with padding. All right, so this is going to be test start, test end. Okay. Well, we've got other tests that are kind of like this, so let's go find one of those. Emits push when number found. That's pretty good. Emits is a nice word. Okay. Emits push when number found. Okay, so some of the same arrangements. Well, I'll just take this for a base, I guess. Okay, so compile test space. Well, there's no. I don't think we even need to do that. I think we can trust our space in it. Now I think we did that. Yeah, this kind of thing. I think all three. Actually, we don't need data stack in it. I don't think we need dictionary in it either. But all right. So let's do that. Okay, so we initialize the space to write to, and now secondary space is pointing in at some location. So I'm going to not worry about this. Load address. Well, I don't know how much I want to rely on read word. I don't think I need to. Let's do L string to compile. And I'm going to make it intentionally short. We'll make it we. Okay. So it's a we, WEE 0, and then we can check that the secondary space really does realign to an 8 byte boundary. Now, normally it would be in quotes like this, and when you compile it, but we're gonna do the work of read word ourselves. Okay, so this, and then we're gonna do a move. X1 gets string found. Now, I don't know if that constant will be defined yet. Okay, and we will compile. All right. Now that much seems good to me. Okay. Now secondary space init. Let's find that. I don't know if that's in here. No. Notice we do have a register for it, so I just have to find that. Stack? No. Compile. Okay, so L secondary space. Well, Okay, we can deal with it. So when we call this, we'll need to save. So we've done this a little. Oh, I'm sorry. Excuse me, just a minute. All right. Well, we'll need to save where that space ends up. And we've done this in a few tests, but maybe not in here. Man, I don't know. This just doesn't stick in my head. But if we use an extra operator, well, I think we have to store the existing value x28 in SP plus 8, not adjusted. And then this down here, we have to restore it with a loader. Okay. Welcome. Hey. So we're working on an assembly language interpreter compiler for a programming language, and we're working on compiling strings for it. I'll go back to the picture in a moment. All right. Okay, so I think we can use x28 now. So what I want to do is capture x28. X28 gets secondary space. All right, so I want to know where it is at first. When it's first initialized. So we can go back there. Let me get the picture. So to put in a string in the middle of compiling something, we're going to put a push, a location, a jump, eventually a new location, and then the string itself. So our test is really, does the first cell contain push? Does the second cell contain this? Dictionary setup does initialize registers, but we're not going to use the dictionary, so we won't have to do that. It basically points the dictionary pointer to the well, it's kind of a null, I guess you'd say, a null link or something, or an empty first link or something. So because we don't really reference the dictionary at all, I guess I should look at the control stack though. That might have space associated. And I do not remember. I guess maybe it's in here. It seems like there should be an initialization for it as well. Init control stack. Okay, let's do that. Okay, so we're using the control stack. We're using the secondary space. We're loading up the word we want to, or the string we want to compile, and then we're loading the type of that index one. Okay. So load address X0. Well, I think we just want to get to secondary space X28. So let's move. Well, yeah, let's move X0 gets X28. And this is points to initial secondary space. And then I think we can just reference incremented off that. All right. So let's say what we're doing. So we're going to check for a push, basically. We'll load the initial space, we'll load what it points to, and that value should be the push word address. Okay, and that seems good. Then we want to see secondary space, which is now eight later. Yeah. Yeah, I think this is probably our last week of low level stuff. We'll probably have to bounce in and fix some things or expand some things, but yeah, we've been doing this for several weeks at this point. Okay, so what I know for the second one is I'm going to start out the same way, basically. Well, we'll make some adjustments, but well, this is kind of close, isn't it? Okay, well, we'll just repeat this because we're not assert equal might destroy anything it wants to. Then we're adding 8, and that tells us where we're going to load from is the secondary address, the second. Okay, yeah, so compiling strings. What will happen, I'm going to run the REPL. It doesn't work yet. Well, it kind of works. Right now we have this notion that you can have a string, okay, hello, and that string gets put somewhere. This is we're down pretty low level, so the REPL the execution environment has to put that string somewhere. And once you have it, the only operation we support right now is printing it. So I guess I can peek at it, hello, and if I print, I'm not going to get hello back. I'm going to get the address of the hello. Okay. Um, so here's some low level memory address. But if I do $, it says, don't treat it as a number, treat it as a pointer to a string and print it. And it prints that string. Okay. But when I define things, okay, so I don't know, if I don't even remember my JavaScript enough. Whatever you do to define things there, if I define a function, colon does that, foo, and then all I want to do is load that string world. And so this function, when I call foo, would just load world, put world on the stack, and then I could $print it, $print it. Now the problem is this thing doesn't recognize it. And so what he complains is, hey, you told me I don't even know what world is. It doesn't look like a function. What's going on? So we've got to do something that when you're doing this definition with colon, you're entering the compiler basically, and we need to make sure that the compiler knows what to do when it sees a string. Just like in JavaScript, I mean, the JavaScript interpreter, when it sees a string, it's got to if you type it in or something, it's got to put those characters somewhere that other parts can point to it and use it. Okay. And same thing here. It's just that we're the ones writing the interpreter for it. So we have to put it somewhere. And our whole thing today is oriented towards making it go into something like this so that it has somewhere to put the string. And then this push means it will leave that pointer on the stack like it's supposed to. So, the goal of that quote thing is to put it on the stack so people can manipulate it as a string. Okay, so if I go back to X28 again, I'm going to add 8 to it because I want the second word. Sure. I want the second word, so I'll add 8 and I'll load X0. now I have this secondary space. Well, I don't know the value yet. I have to look at it. Okay. But I know what it should be. It should be x28 plus 8 plus 24. So it's really 32. Well, it's really, I'm going to say x1 is going to be x28 plus 32, if I can do that. I'm not quite sure if I can. Okay, but we want to check that push gets the string's address, is what I would say that's doing. Okay, now, do I want to keep going? We could take the fact that even though it's just partial, we could stop here, but I think we're going to keep going. All right, and actually this is going to be kind of closer to the next one, kind of a blend of them. Okay, so I'm gonna get x28 again, which is the original secondary space, and I'm gonna check for a jump instruction. Okay, too large value to add with that combo. I'm not following you. Sorry, Mudchug. Trey Guy, welcome. Yeah, that's what we're up to. Hello world, basically. Okay, so we're compiling a string in this language we're defining, and we need to make sure that the quoted string, we need a pointer to it to end up on the stack. So we've got to put the string somewhere and then return a pointer to it. And the way we're doing it is filling in pieces of this. We filled in push, we filled in the pointer here. Now we want to check that jump is there, and then we'll want to check that this points after the string. Okay, so jump, now we're on the third word, so 8 plus 8 is 16. We look inside, and just like this one is closer, I don't want push word address, I want jump word address. Now, I don't know if there is a jump word address yet, but that's part of our test. All right. Check target of jump goes after string, rounded to 8 bytes. Okay, so our jump, we got our jump instruction, but we got to make sure this points to, well, secondary space started here is 0, 8, 16, 24. The string is only 4 bytes, but we have to jump by 8. So 0, 8, 16, 24, 32, 40 is where we should be going. Okay, so this one should be 40, and it's going to be similar to this. All right, we go back to x28, which is the secondary space. We're after the fourth word, 0, 8, 16, 24, and its contents, and they should be x28 plus 40, if I counted right. Let me see if I'm counting right. Okay, 0, 1, I'll just count blocks of 8. 0, 1, 2, 3, 4, 5. So 5 times 8, 40. Okay. And, sorry, we got one more. Well, no, we don't. I guess, oh, we want to check the string itself. Okay, so that should be, check that string is put in secondary. Okay, so again, we'll do this stuff, offset things, get that thing. We want to look at the next word, which is plus 32. All right. 16, 24, 32. Okay. All right. Well, that gives us the pointer to the string that should be there. And we want to compare it to, well, that's that string we started with, the string to compile. And actually, this will kind of do it. Okay, so now we're looking at the right place. It gives us an address of a string, or it's supposed to, and then we're going to call assert equal string. Okay, so I don't know, these kind of long sequences, they're a little tricky. Might be worth something to, I don't know. I always have this tension. I say we're just not doing enough of it to really make this all, kind of macros that know how to check the next step and so on. But maybe we ought to. I don't know. All right. But at any rate, I think that is what should happen. This is all part of REPL tests. I added the test above. Compile already exists, my code I'm calling. So everything's in place. I think we might have a missing name for the jump address, but we'll see. So I'll do a make. Okay, assert equal string is probably assert equal strings. Okay, and there's our compiler tests. Okay, so each of these is saying, I was expecting this, I actually got a 0. I was expecting that, I expected this, I expected that. These are either addresses of functions or addresses of pointers. And then down here, we expected WEE as a string, and it's not there. Okay, so everything's missing, which is what we expect at this point because we haven't implemented anything yet. All right, now we'll go in REPL. Okay, so compile. Well, we do dictionary search, but a string doesn't really make sense as a dictionary search. And actually, the test is almost exactly what we did up here. If I find the string, I want to do something special. Now, I'm just going to copy this and we'll tweak it a bit. But this should be the basic idea of checking for that. All right, so did I not copy it correctly? Okay, so X0 is the word. Now, let's see, REPL. Yeah, we called read word and eval all. Let's get to eval all. There it is. Okay, so it decides whether to compile. Now it, the problem I think we have is we have the input is not just X0 anymore. It's now X0 and X1. And we kind of ignore that. So X1 is the type of word. Okay. And we saved X28 to hold X0, but then we called isMeta, which destroys it. Okay, so, or potentially destroys X1. So we got to store X1 somewhere while we decide what to do. And so eventually it comes down to compiling. We get X0. Okay, so, well, I'm going to find one of these. I know we did this in a couple places, and I'm not good enough to remember what went with it. But some of them used more than one variable, and there's a little twist to that. There it is. Okay, so this one, the standard prologue we use, creates the stack entry for whatever the link register or whatever pointers it needs. Um, the second one can offset by 8 because it we have to allocate 2 words at a time. It's just the way the stack works on ARM64. So that first one was kind of easy. We just reference off the stack pointer a little further. The next one though, we have to allocate another 16 bytes for it, and that's the bang here. Actually, their stack grows down, so we subtract 16 more bytes and allocate another pointer. X1, I don't know why we chose X11. It it doesn't really matter. Well, we can explore that another time, I guess. But I'll probably use a different one for this. But the structure of SP pound minus 16 bang, that's the piece that counts. All right, and the way I decide what to do is we have, I think it's environment notes. Well, it's in here, right? Okay. Um, Standard registers. X19, X28 are reserved for caller. So these, if you want to use them, you got to save them first. So I'll use one of those. So in REPL tests, let's use X27 instead of X11. It probably is a better choice in the dictionary too, but I'm not gonna go back. Okay, and then where was that from? See, like, oh, dictionary. No, where's my search? Yeah, dictionary. Okay, and the restore, oh, is, well, it's a little different, I guess. Okay. Yeah, I agree. If we probably could. I think the advantage for um, picking these is that they're consciously um, designed to be caller saves or callee saves. So it's pretty clear why we're saving a callee saves register because we want to modify it. Um, but you know, ignoring kind of conventions, you can use any register, and that's probably what we did when we did dictionary because weren't as clear on the conventions then. Okay, but at any rate, I have X28, X27, and this one is X27. Let's say X28 points to initial secondary space. X27. Oh, I'm doing this. Not. I don't need this in the test. I need it in my compiler. Sorry. All right, I'll get there. All right, this X28 holds word pointed to. X27 holds type of word. All right, and then we have to do something with it. Gets X1. All right, and then down here, did I save that? Nope. Go back to dictionary. I have to restore X27. Okay, so at this point, all I'm doing different is I'm saving X0, X1 to keep the initial conditions for this evaluation. But now notice here I brought an X28. I really need to bring in x1 as well. So x1 gets x27. Um, restore pointer to word. Restore word type. And then really this should kind of, for symmetry, let's make this the same. But the reality is, no, it is. It is probably a good idea. Okay. I guess I can take that same comment here. I think it's proper that eval gets both these things as it should. Okay, I don't anticipate that breaking anything. Everything that fails should still fail because we haven't written anything yet. Okay, now. Now, in fact, this does break things. Puts found word in secondary space. Let's. I'm not sure the fast way to do this. I would have thought compile would be okay with that. Eval calls compiler in compile mode. Let's track this a little bit. I don't know. Something's really weird by this. Let's make sure this is the issue for these two. I don't think there should be any harm in storing this and then using it. Let's see. Let me go back one to our previous run. Okay, yeah, all those passed before. So my thing I thought would make no change does break something. So, okay. Reuse of allocated memory. It's possible, but it strikes me that it didn't affect it until we changed to X27 and X1. I don't know if there's some relying on X1 that's not visible to us, but let's see what that did. Commented out those. Okay, they're still. So it was fail, pass, fail, 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 then ours. I think that's what we just saw. Go back one more. Fail, pass, fail, fail, fail. Yeah. Okay. So something's going on with those. Let me take this out. And I think it'll be taking that out that does it. And I think I can say make, well, let's try REPL tests.out /REPL tests. Okay. Now let's do X27. Oh, interesting. Segmentation fault too. Okay. I'm going to take this out and this. No. Yeah, let's make sure that's not the case. I mean, because we're getting to secondary space, I don't think that's reusing anything. String to compile is here. Oh, let's make an align here, just in case that's an issue. But again, I don't see how that breaks earlier tests. Okay. And this new one is running last, so it's something else. All right, did I change other stuff in REPL? Well, I thought I didn't at this point. X27, X27, X27. So I blocked out anything that has X27 in it. Let's do a make clean and then make those. Huh. Okay, well, let's check the old tests are before, because it well, I believe. Let me double check. REPL test. Yeah, our new test is the last test. So those old tests are physically before and they run before. So I'm super puzzled by that at this point. Actually, I'm not sure what's going on because I reverted everything to do with X27 and I thought that put us back where we were. Maybe I can check that. Compile. Yeah. Comments. Okay. I added a comment, deleted that. That's nothing, 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 nothing. Okay. Oh, did I not? Maybe, oh, I probably junked up compile. Yeah, this is random code. Okay, yeah, not that copy and test errors can't happen in assembly, but I believe that's what just did. Okay, because I put this in, so I haven't restored myself back to where I was. Let's see, push secondary space. No, that's, let me cut this out for a second. Well, let's just do a make. Okay. Yeah. All right. Yeah. Me being stupid. Sorry. Jump to check word it number. Yeah. So this is, yeah, it's just jumping back to eval exiting instead of exiting compile. So yeah. So I guess I jumped from trying to fix this to, oh, we got to make sure things are in the right place when we get called. Okay. So here, now this string address, I don't think, I haven't said what to do in this case yet. If it's, well, let's put this here. This is where it's got to be. I'll say lcompile, check order number, lcompile, check order number. Okay, so if this thing is a string found, we're going to, if it's not string file, we're going to jump down and do what we always did. If it is string file, we're just going to exit the routine. Okay, and I need to reflect this. This is a change. We put the change in the other day, but I didn't update this. And actually, I don't think we properly supported it in this routine until now, or hopefully. X1 is the type of word found. And I'll say that this pointed to a word. Okay. 125 is the culprit. Okay. This should be no worse. Okay, yeah. So now I've unbroken what caused those to break. We haven't accomplished anything in ours yet, but we'll go there next. Okay. And I'm going to keep an eye out because I think 309 is the eclipse here. So probably 305 will take an early break, maybe a little later break too. But now we're ready to do something. Well, what I think we ought to do is I would say we should just call another routine for this. So let's BL compile string, and we'll make up a new routine. Okay, so text align to, just for care. And we want to do compile string. And he's going to need the standard prologue, I think. Log and return. Okay. So again, that should accomplish nothing. It's calling a routine and immediately returning. Okay, but I think it's on the path. Okay, so when we get in this routine, we get to assume the same thing. X0 is the pointer of the word. Save a string and load its address. And then we have inputs. Okay. And then I guess output is generated code. All right. Now let's make at least the first thing better. So that comparison was basically the push. All right. And again, I'm going to kind of look around. Oh, here's load address, push word address. And this is kind of ish what we're after. I don't know if it's a terrible habit here, but all right. So the first thing we have to do is store push in secondary. Okay, so if we load address, let's use X2 so we're not stepping on ourselves. We're going to store push word address in secondary space and add 8. Okay, we've got a macro for that. Was it core defines? Nope. Something with secondary. I thought we had one. It's not right secondary, maybe. Let's see this code. I think this is the critical piece. What's this one? Store sec. Okay. Yeah. So this is store secondary X2. Okay, I think that's quite an improvement. All right. Address of not yet created string. All right, so again, I think we're going to, let's add x2 equals secondary space, I think it was plus 24, right? Plus 32. Okay, I kind of hate to duplicate, but I think sort of duplicating. Okay, so we're getting x2 in there, and now we want to store that. So this is the pointer to where we're going to write in a second here, secondary space, pointing down for instructions. And let me just double check our picture. +0, +1, +2, +3. Is that what it is? That's +0, +8, +16, +24. Yeah, I think it's 24. Okay, store jump. How about save address to control stack store -1 for now. Okay, so this is control push secondary space. All right, which points where we're pointing. That's where we're going to patch. And then we're going to, I don't know if we can do this or not. Okay. All right. Well, let's see if we're getting in the ballpark yet. So some of these should start passing. Well, store -1, x25. Okay, so I can't do that with that instruction. I have to load it into something first. Okay. X2 gets -1. And we'll store X2. Okay, went fast. All right, first 3 are passing. Good. That's push, secondary space, jump. Okay, this one should, well, it should be -1 for now, but it should get patched later, so that one's not going to be right. And then we want to write the string. Okay, so now we have a method or routine that does some of this, but I think it needs to break out the actual string writing. Let's see. That is define. Define word. Oh, define string. X is a pointer to the string. Adjust secondary space. Okay, so if I pass in x0, well, I think we've done the thing we want here. Points to string, stores it to the secondary, adjusts the boundary. Okay. Right, so you can see it ending, stripping off the bits at the end there to make it go to a good boundary. All right, so I think define string does it if we get x0 pointing to the right thing. All right, now store string in the secondary. All right, but we need to capture the address of store secondary when we start. Okay, so we're gonna need our register trick here. Okay, this kind of thing. I'm not gonna use X. I'll use X28. This uses X28 saved pointer to secondary. Well, this is Do we need that? X0. I guess we don't. I think we're okay, actually. Okay. So store the string. Well, X0 came in with the pointer to the word, and it doesn't. None of these instructions, these macros, are not procedure calls, so they don't destroy anything. So X0 is the right thing now. So say pointed to by X0 into the secondary. All right, so just BL define string. If we go back there, needs that pointer to the string, and at the end it adjusts secondary space. Yeah, I don't think I need to save anything to get it there. It's doing the stuff, I think. All right, but now we have to go back and backpatch target of jump. Okay, so we don't know how long this string is going to be. It could be a short one that's only 1 byte. It could be 10 bytes, whatever the length of it. All right, it's got to go. This jump has to jump around it. Okay, so let's do control pop. We don't need X0 anymore. Well, I can use X2. It's been consistently a temp. Control pop X2, that's where we want to write. And then what we want to write is secondary space. So we're going to store secondary space, the address after the string, into whatever X2 points to. X2 tells us where to write, and secondary space gets written. Do we get a return value from defined string? That's a good question. No. It just writes it and adjusts the space pointer. Yeah, in that sense, yeah. Adjust secondary space. Yeah, this probably could fit on 2 lines better. Okay, so I think we've done everything we need to for REPL. Sorry. Store the push, store the address. We can compute that because we know it's just this plus 8 plus 16 plus 24 gets us to the string. Stored jump. Stored a -1 temporarily, but pushed where it should patch. Stored the string. And then pop that control stack and use that to do the patch on the -1. Okay. Now, I'm not sure why that crash at the end there, it's not a good sign, but it could well be from all the other stuff going on. Could manage compile. Is that where it is? No. What was the name of that thing? Where is it? Oh, REPL, sorry. Oh, yeah, we do still have a failure here. But the good news is 3, 4, 5 passes. So let's check the test. I thought there were only 5. 1, 2, 3, 4, 5. Right. So something's going on. Okay. Well, we can run REPL tests. Let me REPL test.out. And I'm just going to run because I just want to let it crash where it's going to. Okay, so bad access, load our X0, X8 plus 44. Well, I don't know what X8 is. We don't use that one a lot. Reg read X0, X8. Ugh. Okay, so we got a 0. We definitely can't read 44. Okay. Well, I'm going to run outside and see what eclipse I can see. It's only partial where I live, but give me about 10 minutes. Um, what this suggests to me, I wonder if we, I wonder if we didn't store the secondary space plus some offset, and we're just pointing to the offset by itself. Maybe I don't know where this code is either, though. BL diload 3. This may be some sort of exit code. Maybe we didn't clean it up. Yeah, you get one of those midnight eclipses or something. Okay, I will see you in a few minutes, and we'll pick up from here. This is some sort of something's not set up. I think this code, it looks like it's the actual simulator exit or something. So we've messed up something that it relies on. I'm not sure what that is. All right, see you soon. All right, welcome back. Well, the eclipse was a bit of a bust here. It's kind of a gray and rainy day, and we're going like, is it less gray or more gray? Hard to tell. Okay, is there memory space in text instead of data? That's a good possibility. Memory space in text. Well, it's allowed. It's allowed to be in text. Um, we just have to make sure we are in text when we put code. Let's look if we used X8. I don't remember using it for anything. No. X8. Bad access. 44. I don't know where the 44 is coming from. Die load start plus 2368. Which is dynamic load. Mock file is simulator platform. Compare Bazy. Well, we can dump. I guess this is repletest.out. That address, though, I don't remember seeing anything like that. OX19B43. I don't. Well, it's weird. It must be something we've done. Have we used an address without saving it properly, maybe? Because if we trash somebody's callee saved register, maybe. This stuff, I mean, we seem to be getting here. SP add 16. Oh, that's not right. We took that out of the test, but I guess maybe that's all it probably is. Could be a dictionary problem. Yeah, could be. Let's see. I think we just restored a register that they were using or something that throws them off, but that's a theory. I haven't made it work yet. Let's see. /REPL tests. Okay. Yeah, that was it. A little leftover copying, or yeah, I started to make that X27 in here, and then we restored X27 off the stack, but we never put anything on the stack, so we're just grabbing something randomly off the stack and shoving it in X27, and now the stack's off kilter for the return statement. It was probably the link register value or something. We popped that instead of the real thing. So yeah, wasn't good. All right, but the good news is this seems to be running green. Okay, there's REPL tests, all green, no problems. Okay, so yeah, ACP compile strings. Now, what we haven't done is really see it work. But we did, I think we did enough that it should. So, whoops, make REPL. All right, so if I define foo is hello world, and then return, or yeah, return, or end the definition, that should create the code for hello world, create the string for hello world, and load it onto my stack. And if I do that, oh, still not getting that. Yeah, so I don't think food's going to be working here. I did notice something different though. The last time it did that, it left it in red, and now it just made that red. I thought I did, but maybe I didn't. I must have if we're calling compile string. Because our test just calls compile, so I think it would have to be calling compile string. But let's look. Okay, so we look x1. If it's not equal there, we jump to L compile check, otherwise X didn't compile. Okay, so I think we do in fact call that. No. Okay, let's do the equivalent. If I do bar is 7 and I call bar and I print, I should get a 7. Okay. Well, let's check who calls compile. Make sure they give x1 the right advice. Well, there's eval all. Let's go up there. Oh, well, okay. That code we wrote, I think we actually needed it. So this should be that. Define foo is hello world. Boom. Huh. Let's do that again with a short word. Maybe there's something wrong with that stuff. Foo hello semicolon. Boom. All right. REPL that out. Run. I guess I'll do that again. Foo hello semicolon. Boom. In compile string, store x25, x27 offset by 8. Compile string. Well, there's the x2 gets -1. X25. global word 112. That's kind of hard to know what that means. Store X25. So this is right before define string. Okay. I guess that's that. Store X25, X27, and then offset by 8. X25, but X27 is not. Yeah, good idea. Run that. Yes. Okay, so if I do this, $, yes, colon foo, we. So apparently X27 is weird. I mean, 1 is not a value it should ever have. X27 is our secondary space, right? Oh, no, that's X25. Oh, X27 is control stack. Oh. Is that what I used? X27? X23 is free, X27 is not. Okay, yeah, that's what's going on. I used that for the temp and then I tried to use it and it destroyed it. Why it didn't show up in the test situation, I'm not sure. Actually, no, I bet our tests have problems now. Make REPL test.out. No? Okay. But yeah, there's a collision, so let's straighten that out. X29. I'm not sure where the collision is, though. Oh, eval all. Yeah. Okay. Uses X28 and X23 is temp holding type of word. Now, I guess compile does need that. Because it's got to check whether it's got one of those first. Okay, so I was worried it didn't really need it. Actually, evaluate probably does not. Let's see, evals up here. Oh no, it does. Okay. All right, and then X23. Okay, X28, X23. I don't see any X27s. Let's do a make. Good there. All right, colon foo. Hello. Semicolon. Yay. Okay, now I do foo. Should give me should push the string on the stack. If I do dot, it's junky, but if I do dot $, hello. Okay. Ooh. Alrighty. Okay, so fix register collision that made it not work in REPL. I don't think there was another aspect I guess it was a little odd that it still worked in the test, but yeah, so yeah, I'm a little puzzled why it worked with X27 kicking around. Oops. Thank you. Um, I'm a little surprised the test worked, that it didn't hit the same condition as the REPL did, because the test assumes that there's a control stack. I mean, the new code we wrote, compile string, assumes there's a control stack. So how it would get by with that being um, the word type, I don't quite get. But I think we've straightened it out anyway. All right. So compile time string constant. Well, I don't think we need that in the permanent file. Eighth, right? Ooh. Okay. And then I guess it's just which things are worth doing. I don't know. I'm gonna say we definitely want split, because that's how you'd write a loop to go through a string. And I think we definitely want make, because that builds a string from an array. I don't know. Um, let's check that. Well, I put the X27 in temporarily, but it doesn't need either one. It doesn't. It's seeing the result of control stack, so the test code doesn't isn't affected by that. Only the compile string code was affected by X27. I mean, it's on the one hand, these kind of things do happen, that some random, well, semi-random value could be interpreted this way or that way. But I mean, I don't know, I wouldn't say careful exactly, but I definitely started the test to run compile, um, because there is a lot of code between the compile. Well, maybe that's the reason though. Compile has to check X1 and go call um, compile string. Maybe it was something between the eval all and the compile that did it. Is kind of my theory, because compile all is where we were actually making a lot of changes to. Or eval all, sorry. That's the one that really was messing with the flags. So all that X23 stuff, X27 stuff wouldn't have affected the test, right? Because we called one level down from here, but but the REPL really does do that. So I think, yeah, it's in effect the test started in compile mode, uh, in the sense that it didn't go through eval all to get there. We just called it directly. So I think that makes sense to me, that um, eval all was actually destroying the control stack that compile relies on, and changing this solved that. Now it should. Well, I'll tell you what. Let's make the test call eval all. Is there any setup it needs? Compile flags is meta. Well, string is not meta, is it? I guess if we're in compile mode, we skip. If it's meta, we skip. Is that right? Okay, so if it's we and the photo flag with compile mode, and if it's not compile mode, we go to evaluate. Then we check the meta word. Sort of 1. If it's equal, well, that certainly should have a constant. I actually thought we had some. That's the registers. I don't know about assembler now. User functions. Well, I think I had them at one point and things weren't working with them, and so I took them out. .eq. Right, there's meta. Oh, right. Okay, pound that code should be good then. But let's use meta. REPL meta. Okay, so if it's meta, it never compiles, it always evaluates, right? So meta words always run in eval mode. Okay, so if you're not compiling, then we'll definitely go to evaluate mode. If you are compiling but you're a meta word, well, we evaluate you anyway. Otherwise, you're a regular word in compile mode. Let's do your stuff. And we call compile. Okay, so I think I can do this. If let's make our test call eval all. And I think it will pass now. Oh, nope. Okay. So there's some test setup that's missing or something. And we designed our test to call compile, so I don't know if that's... Yeah, he would need dictionary init and all that then. But maybe that's all that would be. Is it dict init? Yeah. Okay. I guess we want to find a test that calls eval all. And is that the one we just did? Yes. Okay, there's one. Dictionary init. Eval test stack. I don't think we need our stack for this. No, our test does not need the stack. Okay. All right. So now we'll try dictionary init. And hopefully this test passes. No. Eval. Oh, is meta? Yeah, this would require a bunch of setup. Okay, I think I'm going to leave the test where it was. Because is meta requires not just the dictionary but also the meta word dictionary. There's already an error handler that's default setup. So okay, but I believe, I don't know, that convinces me that the issue was the path for the top level path when we ran the REPL goes through a val-all that was trashing a key register, like that's pretty clear. That clearly was happening because X27 was the dictionary pointer, and we definitely need the dictionary pointer to run a val-all. So I think it hangs together to me that that caused the failure. Our test tested a level lower to make sure the compiling was right, but didn't test so much about how to get there. Um, but in general, I think, well, we don't actually need this for that. So let's put that back. Okay. I mean, I guess I find it pretty convincing to me that we trashed one of our 6 or 8 control registers um, when we run the REPL, and that is why that crashed. Normally we want to make sure if our test passes, our code works, But I think we have one of those gaps, and I think we can let it go. It's kind of well, it means there's something untested for sure, but I'm gonna let it go. Take your advice. All right. Now I think that puts us to the next thing. So I don't know. I want to do like bare bones. I don't want to put every string operation in. And split lets you join a loop, run a loop, and then the loop can decide what to do on each character and all that. So I think that's um, that's probably okay. I mean, I would say that's kind of a bare minimum thing. A join is kind of handy. Make was my thing that takes it from an array, and you almost could have something that puts it in an array. um, and then at plus was character by character access. And all of these are just like you kind of can do something. Um, try arrays of strings. Yeah, I think. Well, I don't know. The problem I had in mind, I'm not even sure where I have this thing kept at this point. Um, I have a sort of puzzle thing. You take a phrase like a quotation and you write it in a series of boxes on multiple lines, and then you take anything that's not a space in the quotation lines, and you just look down the column what letters are in there, and you put those in the column above. So each kind of vertical section ends up in a column up above. Then you clear out the quotes, and you're just left with black marks for the spaces. And the idea is you're gonna look at those letters up top and say, oh, if I took the first letter from the first column and the second letter from the second column and the third letter from the first letter from the third column, that's THE. I'll bet that fits as a word in my game, in my puzzle. Um, but I don't know. That might not be. Yeah, I don't know. To do that, you basically have to break up strings, kind of character by character, and put them in places, and then put characters in and match them back down, and then reassemble them and stuff like that. So there's definitely some string-ish operations, or at least character operations from strings. Not a lot of stuff to like you're not manipulating a character other than like make it a space or make it not a space or something like that. So um, or the other one is a calculator kind of thing. Um, hmm. I don't know. Maybe that should just wait. Although split gives you the ability, right? Because you can get to a string. You can't rebuild a string. So join string would do that. Yeah, I mean, you probably could. Oops. Um, you probably could do something with just join. I mean, if you had both split and join, you definitely have the ability to create any arbitrary string, um, or make. I guess you got to be able to get from a character to a string somehow, right? If that's the way you're going. Um, and you can always. Hmm, I don't know. This is yeah, this is kind of one of these things, like, just how far do I want to push this stuff? I don't think any of these are too hard to write, and maybe that should just be good enough and do them. Um, make could be used by join or split. Well, what I had in mind for make was you would have an array of numbers where the numbers represent the byte, the characters in the string, and the last number you care about is a zero, and it would take those numbers and pack them into a string and return the address of the string. Um, join, I was thinking more of, I think I had in mind join just being kind of a string append, but I may have thought of it as the opposite of split, to just reassemble a character to the front or back of a string or something like that. But append would be a better name if it was the back. Um, yeah, so I wouldn't even put them on the stack. They would do, what I was thinking was an array that you would, basically, that you could fill up this array with stuff from, characters you wanted to write into the string, and then boom, make that a string. Um, putting 64-bit values on the stack. I mean, that's another way. I think you mentioned something on that line last week, maybe, or something. We could say, yeah, put a bunch of characters on the stack and then pop them all and append them together and make a string. Maybe push a bunch of character or a bunch of integers and a count, and then say, convert to string from stack, whatever the word would be that would do that. Um, yeah. So, hmm. I I feel like this is a thing. It's not hard. Sorry, two messages from the same person. Just make sure it's not anything hypercritical here. Um, all right, sorry. All right. I think we can put those off. I don't think they're hard. That's the real thing. That's why the decision's so silly in a way, because they're fairly easy. Um, any of these would be, less than a certainly less than a session to do. So in that sense, like, I can just wait and see what we need when we get to our project and then put that in, because I'm not trying to build the perfect library of string functions for this language. I just want to get enough in there to do proof of concept and develop something. I'm sure we will need something, at least split, or at least some sort of append a character to a string kind of thing. But yeah, if you have an array, you can push the values and call make. Yeah, one way or the other, it should be an equivalent, as long as you know how many either you look for the zero, or you know how many to try, or some mechanism. All right, it's kind of weird to push them from right to left. So yeah, a count's probably easier. But I do think any of these would be a relatively simple thing to do, and I could make up, 10 different string functions, but odds are we only need a couple for the work we're going to do. So I'm going to defer that. I may regret that because the thing I want to do instead is this. Uh, I'd like to know if we can do this, and I think it's going to take some experimentation. Hangman, that sounds fun. Yeah, let's do Hangman. Okay, so yeah, you could, if we can read something from a terminal, you could build up your words as a little program, and then suggest the word, character by character from a terminal, and something to draw those characters um, in a shape. I don't know. We can work out something for that. All right. Let's see. So this one, I did some research. Now, where did I put the research? That's a good question. Oh, here we go. Okay. So I don't know. So um, the command in the system level call in Unix to do stuff to the terminal or lots of other things, but for IO is IOCTL, IO control, and um, basically terminals, they have this notion of, they sometimes call it cooked mode and raw mode, and then there's sort of a half cooked mode, half baked. Um, Cooked mode is the normal mode that you get in a terminal. So I start typing um, hello world Wordle, okay, oops, and I hit delete, delete, world. And like in this terminal, I hit Control A, go to the beginning of the line, Control E to the end of the line. I can do my arrows, all that kind of stuff, and I can that is the cooked kind of behavior. No, all the editing on this line happens, and then when I finally hit return, that's what that's what gets sent to, in this case, the shell. Now, another thing that happens is Control C gets detected. So I hit Control C and it killed me out of that line. All right. So the opposite of the cooked mode is raw mode, and raw mode is kind of getting one character at a time. And so presumably implementing cooked mode is done with raw mode. That I typed one character and it echoed it, and presumably put it in a buffer somewhere or something like that. Um, so yeah, so raw mode, you do the right IO control statement or call, and it says, okay, don't don't buffer all this input, just directly receive it as it comes. And then it's sort of a separate issue about should I echo or not. And think of writing a password. If I do sudo and I need to enter my password, it well, some versions will put stars and some versions will just put nothing while you're typing. So it's it's definitely not echoed, but it's definitely interpreted or input. Okay. So I don't think we get key presses per se. I think we get what we kind of get. Well, I think we get we get ASCII letters, and some things you would input create more than one letter. So if if I hit an arrow, the terminal actually puts out like escape left bracket H or something. I can't remember what the exact thing is, but it's definitely escape left bracket stump something, which comes from VT100 terminals from years ago and maybe from earlier versions than that. I don't know. Um, but there are certain escape sequences that will come, and you'll receive those one at a time. Oh, ESC, and so on and so on. Now, I've used I mean, like microcomputers that do this stuff. I don't know, back probably 20 years ago now, but um, those would often give you real. You could some of them you could get real key presses, or you would get this key. So we did stuff with the Commodore 64 and the OSI Basic. I don't know, a couple of years ago we did a project with that, and the input you get there, it's like they'll give you things like this. the keystroke I just read was in column 1 of your keyboard. Okay, and I would look at my keyboard and go, oh, it's either escape, twiddle, tab, caps lock, or shift, or maybe, column 3 is 2WSX, whatever. And then it would give you the row, this is in the second row. Okay, oh, then it's 2. Um, and they really were kind of key presses of some sort, raw, just like electrical line, it was wired in a matrix and tell you which row and column it was in. Escape is definitely one you can get. I'm not sure what backspace gives you, but it gives, it'll give you something or it'll be ignored or whatever. Okay. The other thing on that one is if you control C in raw mode, it doesn't just automatically call send the signal that says exit this program, say it, you have to, whatever's reading your raw mode, that aspect has to interpret and say, oh wait, control C, I should call sigterm or whatever the right signal is. There's also this intermediate half-baked one. I think usually I see it called C break mode. I don't know if the C is for control C or control anythings maybe, but that one does interpret control C and say, oh, you should call the right signal. But other normal letters just pass on through as if it were raw mode. Okay, so that's kind of background of where we're going, and now these things I found. Let's see. I guess we'll start with IOCTL. So let's look up this link. Oh, I guess I didn't even give myself a page to look on. All right. All right. So this is the IOCTL call from. Well, it's a BSD call. So, but it's Mac documentation. It's from Apple dev.apple.com. Okay. So IOCTL, you give it a file descriptor, you give it a request that's some sort of long, and you give it a bunch of other stuff. It's like we're gonna be experimenting to figure this stuff out. Okay, manipulates underlying device parameters of special files. So in Unix, you have normal files full of data on your file system, but things like terminals and MIDI outputs and network cards and all that stuff are called special files. And normally they're files living /something/something/something will get you to the TTY, the terminal, or we'll get /something/net gets you somewhere, and so on. So all these various things, this is kind of one of the unifications Unix made to say, let's treat everything as a file. And I mean everything. Okay. And so terminals and all this other stuff get treated like files. Okay. Special files, e.g. terminals, yeah, like that's what we need, are controlled with this. FileDesc must be an open file descriptor. Okay, so this is the normal, 0 is output, I think, 1 is input, 2 is standard error. When you're doing your redirects and stuff like that, that's the file descriptor for the open stream that we're reading from, like at the terminal kind of thing. By default, I mean, Unix has all these ways to hook up other stuff, pipes and whatever. So we know the input descriptor, I believe. I always mix it up because I want 0 to be output and 1 to be input, because 0 looks like an O and 1 looks like an I. But I would have to check. Okay, a request has encoded it whether the argument is an in or an out, and the size of the argument in bytes. Macros and defines are located in sys/ioctl.8. If an error occurs, you get a -1, and errno is a kind of a predefined variable for that. Okay, and then what messes it up if it's not a file descriptor, if the request is bad, if the file descriptor is not actually open, or if it's not a character special device. Okay, so maybe if you used a file, it would fail. The request does not apply to the kind of object that the FileDesc describes. Okay. The rest is kind of historical. All right. So, wow, even that is 27 years old, something. 30, 31. um, we will be calling this because this is the function that it's the Unix function that does this. All right. Now, next page. Okay. In C, or, well, at least in normal C use. So I don't know if you've ever run across the curses package, but it gives you sort of a pseudo graphical window for character based or for terminal based applications. So in your terminal window, um, it will keep track of what position you're in, what row, and all that stuff. It can jump to a given column or row and move there and write more stuff and all that kind of thing. So you can make a it's not graphical, but it's like a graphical app in some way. You could put the input box here and so on. Now we have this tcgetAddr. All right, so a terminal. This is a function that's part of sort of the C library, I think. Yeah, GNU C library. Okay, good. So the gets GCTT, whatever we call it, tcgetAddr is like terminal controller get attributes, and it's got a bunch of flags basically that you can read to find out what the setup is on your terminal. Now I don't know half these things. We will find the documentation for it, but this is, it's filling. How do you get the attributes? Well, you do an inline syscall of ioctl. So this is basically the call we're going to try and make if we can figure out how to set it up. Okay, now here's this last one is ktermios structure kernel terminal IO system is basically what that is. That's a block of memory that we're going to be manipulating. Okay, so tcgetS is the code. 54 is a magic number, 5401. Okay, we'll have to find where those are. So, I mean, we're in for a day of research, basically. We'll get as far as we get today. But what we see is it makes the call, it gets back this K terminal structure, which, that's defined by Unix. And then it has this termios structure. Well, again, still defined by this, but we can use it. Okay, so here we go. Termiosp. I think this one may be a C library structure. And this says, I'm going to copy the CI flag from the kernel's CI flag, and I'm going to copy O flag and C flag and L flag and line are all going to get copied from whatever the Unix call returned us. So that gives the C library some isolation in case this ever changed. You'd have to update this routine, but the structures that everybody else relies on would not change. Then there's more. What's the speed? So you can find out if it's 110 baud or 300 baud or whatever, it mattered a lot more back in the day. Let's see. The speed is not consistently treated across Unixes, so there's stuff around that. Okay. And then I'm not sure this last bit, memcopy something. So there's some other structure that's getting copied in there. Yeah. So this is the kind of code we're going to write. I'm not going to get so fancy. Mostly, we just need to find out we need to find out I think it's two flags we need to set terminal into raw mode. We want to control raw and echo, I guess, or character by character input and echo. Now, the way you use this is the first step you do is you call tcgetAddr, and whatever, like you're probably in cooked mode the first time you run, and you need to call that and then save that value somewhere. And then you call tcsetAddr to put it into the raw mode or whatever kind of combination you want. And then at the end of your program, you call tcsetAddr again, but this time you call it on the original that you saved. So you restore the terminal ones. Otherwise, when we exit, we'll still be in raw mode. And I don't know how we're going to do that, but we'll figure something out there too. All right, next one, tcsetAddr is similar, but we'll take a quick look. Okay, so I'll just leave these on different tabs. All right, again, IOCTL and so on. All right, term IO structure used by the kernel is not the same one in libc, so we must translate it. Okay. We need to know the kernel one. Okay, this is a gross hack around a kernel bug. If CEF set iSpeed is called with speed set to 0, that's different. Okay. We use an unused bit to keep track of this usage. Okay, so yeah, there's a little weird stuff going on. Now, mostly it looks like, okay, well, the I flag is the I flag and not IB odd 0, whatever that is, and so on. But we're setting the kernel values based on the term iOS. So term iOS is the C library structure, and kterm iOS is the kernel library structure Unix uses. What I get from this is we're going to have to go find struct kernel term iOS on the Mac and figure out like how many bytes do we allocate for this thing. I mean, I could probably give it like 100 or something, but I noticed there's a mem copy here. Whoops. I didn't know those were live. Okay, there's a mem copy. We copy stuff from term, or we're copying into term iOS from copying into the kernel term iOS from the C term iOS. And it's kernel NCCS times size of CCT. I don't know what CCT is. Unsigned character. Okay, well, that's 1 byte. And then kernel NCCS. Oh, okay. 19 something's characters. Okay. I don't know what those control characters do. Now we're going to look for, yeah, you hope the program doesn't crash. Yeah, I've definitely hit those before. All right, but we can see these are flagged. He's unsigned int. Okay, well, who knows what they mean by unsigned int, right? It used to be 16 bits, and it could be 64 bits on ours. So at least, or at most, I'm certainly expecting 1, 2, 3, 4 4 16 bytes plus a character and 19 other characters. Okay, 20 characters. I don't know what we're going to find on Mac side. This could be 16 bits. It could be 64 bits. It could be 32 bits. I think I saw something that you could choose, but I'm not sure how you know how you chose. All right. Next. Okay, term IOH. This probably is that structure. We kind of saw it at some point, but yeah, that's where we were. Okay, yeah, so that's the kernel structure. That's what IOCTL uses. All right. And then term iOS, this is probably the C structure, which I don't think really concerns us as much. Okay, but okay, so this, yeah, so these B's, I'm sure they're baud, hang up is 0 baud. 110 was a very common one. I knew there was 75, but never used it. 300 was very common, and then all the others were used at some point. I don't think I ever had to worry about terminals actually being those. They don't really care what baud rate is. But if you had a remote modem, int is the size of the registers. Yeah, I mean, it definitely is a choice thing they could do on their mapping. This is not. I mean, this is glibc, right? So it's not anything that's going to constrain the Mac. There are differences between, like, at some point they had a renumbering of all the system commands, and Linux went one way and Mac went another way. So they're not fully compatible that way. These structures, I think, are likely to be somewhat similar. Now, I was hoping for a little more explanation of these values. Okay, TC flow. Oh, that's something different. Um, Flow control is, you used to be able to hit Control S to stop a stream of output, and Control Q would let it roll on. So I'm sure that still works in the terminals, but I don't think we need to worry about that. Um, Otherwise, I don't know, TC flush. Yeah, you can. I think this controls whether, when you exit, if they're unused, unprocessed letters, do they get left so they're sent on to the command line, or do they get chewed up so they don't? Two baud values on the top end on my modems on the Amiga. Oh, wow. Yeah. Yeah, I mean, yeah, 9600 baud was very common for a while. It just kind of worked its way up. I mean, I know I used, at some point, our school had the old teletypes, with um, a little paper spool printer, punch tape kind of thing. And I think they were gosh, they might not have been 110. Could have been smaller. Um, but these are all relatively common modem values at various points. This probably is, they were like something something 50 terminals, so maybe that was 50 baud. I don't know. All right. Yeah, I was really hoping to see what those flags were. Now, the kernel timer iOS doesn't tell us that either. So, that's kind of unfortunate. I don't know. Let's see TC flag T. I think it was just unsigned int, right? So, okay. Oh, this might term iOS. Interesting they would go to term iOS. Oh, also, it sounds like there's a bits term iOS and a radio term iOS. Maybe I should go to that one. No. Okay. All right. So whatever those values are that we need, we're going to have to find them somewhere else. Now, I don't know if I had another page. No, none of this does that. Okay. So I think what we'll do is we'll keep moving through this and figure out, like, what what do we need to figure out. That's where we are. This is very more of a spike than anything. We might be able to write a small bit of code that we plug in that uses it in raw mode or something. I don't know. We'll see. Okay. Well, let's see if we can figure out IOCTL here. Well, there's IOCTL.h and compat.h. Yeah, so T start C and stop C, that's that control S control Q thing. Interrupt might be, there's a keystroke for that. Stop sending data. Oh, yeah, yeah. Okay, none of these are output speed, erase and kill. Yeah, there was a line kill. Um, Gosh, one of the best terminals I ever used, where um, they had a button kind of on my keyboard. Now the control key is on the bottom left corner. the old, I think it was VT100s or one of that era, maybe a next era or something. They had a line feed button in that corner, and it was default was like delete the last word, and that was actually pretty handy. Okay. Oh, here we go. Half cooked mode is C break mode. Okay. Send stop C on out Q full. I guess this maybe is some sort of automatic pause while the thing is full. But here's echo mode. Simulate lowercase. Yeah, you had a mode you could put it in lowercase, but here's raw mode. No IO processing. Parity bits. My goodness. Yeah, everything. Um, yeah. So I mean, somehow I expect hex 20 and hex 8 will come into what we do. Um, these constants have the same names, so don't use them at the same time. Yeah, okay. Well, TTY was teletype. I know the first versions of Unix ran on paper bowls. um, okay. So, well, this file seems kind of useful. Um, let's see, ioctalcompat.h. All right, so let's start adding information here. I'll just do bulleted. Okay. Local file. Nope. ioctalcompat.h defines raw and echo. Now these other things, I don't think they're going to be useful for us. Okay, so raw is OX20. Echo is 8. Okay. Let's find, well, there's ioctal.h. That's a good one to look at. TTY.com. Okay, pun for the Son of West Predator 3. Oh, okay. So this gets you the number of lines and columns, and I would guess maybe the cursor position. Okay. Well, that's actually not so useful for us. Okay. Let's look for kernel term iOS. Oh, not here. Let's look for term iOS. That's a C file. Now this should look like, oh, this is, okay. I've seen iCanon used for some of this stuff too somewhere. Unimplemented features, okay. All right, I don't think those are too useful. Oh, these might be. Dumping ground for other state because I look like they belong in the input flags. Okay. Echo E. Enable echo. Well, that's the same number as we had before. Echo PRT OX20 is visual erase mode for hard copy. I don't know. That doesn't sound. Oh, iSig. Okay, so this is Control C. I think is quit. I don't know what interrupt is. It used to be some is on escapes. Okay. Um, Darwin specific. Okay. Not define POSIX or define Darwin. Okay. So echo still seems to be that. I don't know. Well, I'm not going to worry too much about this because we could always kill the terminal if we had to. Canonicalize. Okay. Yeah, I think that's the one that does the editing as you go. So I think we may be turning off iCanon. We may negate this bit to turn off some aspects. This file is termios.h. $1,000, was it? 100. Well, there's termios. Ooh, LP64 version. TC flag T, user TC flag T. Okay, so I don't know how we know which one we get. Turn is a term. Okay, LP64. I'm not familiar with that name even. Okay, oh, long pointer 64 data model. Compatible with Intel's library. Okay. TC flag T and speed T are long. Well, I mean, this might be. It's certainly conceivable to me that this structure is the one used in the kernel as well as at the C library level. Oh, and a 32-bit version, just in case we don't have enough. But boy, that looks like what we saw before, right? COFL and CC, but the other one had a character and then CC with the 19 or whatever control characters. I don't know where that constant comes from. Number of control characters, maybe. Mm-hmm. 20. Okay, so that's sort of the same. Okay. I don't know how to find the kernel stuff. Oh, thank you. Okay. Term iOS.h. Okay. So, I mean, what I'm seeing is sort of three different versions of. Did I lose it? There we go. Three different versions of termios. TC flag T is unsigned long on this system. It was just unsigned int on the other. User TC flag T is a 64-bit int. And then uint32 is presumably 32-bit. So I don't know how we're going to know what comes back in this thing. um okay. Now, let's see if there's an ioctl. Oops. Ioctl.h. Did we already look at that one? Suspiciously wide. Okay, yeah, that's the one we saw. He doesn't have much. Because, goodness, guys. Like, what's this request? You know, how do I know what to do? In sys ioctl.h. I don't think that's what I saw there. Request has encoded in it whether it's an in or an out and the size of the argp in the bytes. Octal request. Mac ioctl example C. MAC address, no. Deprecated. Well, IFNet is network interfacey stuff. Oh, there's sockets. Well, we're in kernel documentation, BSD architecture. I haven't seen IO. We'll look for term iOS. Okay, I think that's going to give us. Okay. Oh my. Right? I mean, I'm fine with all those, but I don't know. This is one of these documentation, documentation kind of falling apart on things. The description of IOCTL should completely contain something, a full explanation of the request types and all that stuff, and that's not what we're seeing. Maybe I'm just not looking in the right place, but this is pretty wimpy documentation. And I know we don't usually work at this level. Kernel data types, okay, dioctal. I mean, I'm not even seeing the plain ioctal call fields. I don't think we want network. Don't want mass storage. Miscellaneous file system, maybe. Network, no. Virtual file system, deprecated. 32-bit version for 32-bit CPUs. Yeah, I think that's probably true. I mean, I think we can guess. Well, I mean, I make my guess. My guess is just like kernel term iOS seemed to be darn close to term iOS. I'm going to guess that's the way we do it. Now, this request, we had an example somewhere with a request. Yeah, this thing. TC get S. Ioctl S. Okay, let's try that. Ioctls. Yeah, this one doesn't have that apparently. Well, no, that's not true. I think we saw this one before. Open with Xcode now. About text it. Okay, so this example, well, let's go see tcgetS. What file is this? Octals.h. Well, those all come together. That could be the same. What is this one? Code browser, glibc. tcgetS is 5401, setus is 5402. Octal, hex, good. Yeah. Okay. All right. So, well, one experiment would be take, well, I would say we could write a C program that uses tcgetAttr and tcsetAttr, maybe just a loop that like prints the name with brackets around it or something so we can tell it's really being manipulated. Print each character as it comes. Maybe print each character in a line feed would be something. Um, Call tcgetAttr, save that value, go into our loop that tries to read, exit the loop, call tcsetAttr. Okay, I think that would be an interesting enough C program to write, and I think that's what we'll start with tomorrow. So let's see. So write a C program using tcgetAttr and tcsetAttr. Get, save, set to raw mode, run loop to echo characters 1 per line. And then restore attributes on exit. Okay. Well, if we can do that, that'll be a step forward. I mean, we're not afraid to look at assembly language dumps of C code at this point. We've looked at enough of our own, and I don't think it'll be too hard to see what getAttr and setAttr are doing. If they map those kernel structures pretty closely to the C structures, I think we can just pass the similar block of memory and hopefully get the values we want. Yeah, hacking in the in the old sense. I'm really disappointed that they don't give us the instructions in the manual pages. That's, I don't know. I guess it's they really want to discourage it. But someone was saying the other day, it's like they really have de-emphasized how much Mac OS is a Unix over the last few years, and maybe this is an example of that. But I hope we can do it in C, and if we can do it in C, we can pull out code that will do it for us. All I believe we got to do is call the kernel, get the right block of memory, flip a couple of bits, and call set, and I believe we'll be in action. So hopefully we get there. Okay, I mean we have a language without reads, but it's a little boring. Or we could probably do some sort of um, only read cooked mode kind of things. That's okay. All right. Well, thanks for joining. I'll see you tomorrow, I hope, or some other time in the future, 2 to 4:30 Eastern Time or 6 to 8:30 p.m. UTC. I'll also point out I do a weekly kind of summary. This one this week was kind of long because I went through all the stuff to do compiling of if and while, but that's available either on Twitch or on YouTube. So if you check my channel on either one, you can find those if you have a spare half hour and care deeply about this. All right, take care. Good night.